we have this property that if we have two things equal to each other, we can take both sides to any power that we want. And that's going to be useful when u or v involves some radicals, because then if we have something like the square root of 2, then we can square it and eliminate the radical. So just as a little warm-up, why don't you try solving that one? Okay, 215. So that's right. All right, so basically you isolate the radical. So in this case you add 2 to both sides. And then we're going to cube both sides to get rid of that, the cube root of 3. And so then we use all of our fingers to figure out what 6 cubed is. And that's 36 times 6 is 216. And then subtract 1 and we get 215. Okay, now we're going to go through several different scenarios where we're going to have more than just one radical in it. If we have one radical, it's pretty straightforward. We just isolate that one radical and then do whatever we have to do to get rid of that radical, take it to a second or third or fourth power or whatever, and then expand the other side. Now, if you have two radicals, it gets a little bit more complicated, because if we just took the two radicals here and we squared it, for instance, we would get essentially 3 terms, right? We would get the first term, that's the square of the square root of 3x plus 4. The last term would be the square of the square root of 4x plus 3, and then we'd have this middle term that would be the product of those two. And so we're not making any progress by doing that. So what you do when you have more than one radical is that you choose one of them and you isolate that radical. And in this case, we get a real nice, convenient thing where we have a square root of an expression equals a square root of an expression. And so if we square both sides, it just goes away and we have a nice linear equation. And so in this case, if we take, subtract 3x from both sides and subtract 3 from both sides, we get x equals 1. And then of course we check by putting it in our original equation, and we get 0. Okay, that's pretty straightforward. So why don't you try a couple of these? Just removing the square roots, and then we solve and we get x equals 5. What didn't she do here? Didn't check it. Okay, so let's check it. 2 times 5 is 10, minus 7 is 3. 5 times 3 is 15, minus 12 is 3, so we get the square root of 3 equals the square root of 3. Very good. Okay, so then let's look at Carlos's work here. Okay, so isolated one of the, well, actually brought it over on this side, so he has a radical on both sides and then squares it. And here the point was he did this right. You know, he squared the 3, and that's the easy thing to forget. Sometimes you're just removing the square root, but you have to square the 3 as well. And so then you subtract 3y and then divide both sides by 6, and you get y equals negative 5/6. Okay, so I don't see any checking. Anybody check this? That's right. Okay, when we stick the negative 5/6 in here, we get an imaginary number. We don't get a real number. Okay, so numerically he went through the thing okay, but didn't check the answer, so you know we have a no solution. So just for the sake of the notes, and there's that squaring that 9. No solution because you can't take the square root of a negative number. Okay, so I want to take you through a few more examples. Now, everything that we've had so far has the variable inside the square root. Now, when you have a variable both inside and outside of the square root, you're going to get some different kinds of things happening. So in this case, we're going to follow the exact same procedure that we had before, where we're going to isolate a radical and then remove the radical. So I'm going to subtract the square root of x from both sides, or add it to both sides, I should say, and then subtract 6 from both sides. And so I get my square root of x isolated. Doesn't matter which side you're on. If you wanted to subtract x from both sides up here, then you'd have to divide by -1 because you really do want this thing positive. Okay? So at this point then we square it. And so when we expand that binomial that's squared, we get x squared minus 12x plus 36 equals x. So we need to solve this. Now, if you factor the left side, you're going to find that you just undid what you did. Okay, it factors to this. What we have to do is we have to set it equal to 0 so we can use the zero product principle to tell us what the solutions are. So I'll subtract x from both sides and I get a new equation, x squared minus 13x plus 36. Anybody know how that factors? Okay, so it's not just 9 and 4, it's -9 and -4 because we have plus 36, which means that the signs are the same. We have minus 13, which means that they're both negative. And so we have x minus 9 and x minus 4 equals 0. So we have two possibilities for a solution here. All right, so everything was done properly. So the next thing that we do is we check our solution. The first one, if we stick a 9 in there, 9 minus the square root of 9 is 6, so 9 minus 3 equals 6. That works. And here we have 4 minus the square root of 4 does not equal 6. 4 minus 2 does not equal 6. What happens often is that you'll notice that if this sign was different, if this was a plus, it'd work out. And very frequently when you get no solutions to these things, it's usually, you can usually spot something like that where you have a plus instead of a minus or vice versa. And that comes from the fact that we're squaring these things, and so there is the occasion of losing what that sign is, what that sign should be. So there's really no way other than cleverly looking at the equations to detect this. What you do is you basically go through the pattern of solving it, and then you'll have 0, 1, 2, or however many candidates for solutions, and then you test them, and then you check which ones work and which ones don't work. Okay, so x equals 9 is the only solution. Now you don't have to write that like that. You just put x equals 9 as your solution and put a box or a circle around it or something like that. It's not good enough to leave it like this. Okay, what you have to do is demonstrate that it doesn't work, and it would be fine with me if you just cross that out or if you just rewrote x equals 9 and put your box around that. So, you have to make sure you actually throw away the solution that doesn't work. Okay, another example, sometimes you have to go through it twice and square it twice. And this happens when you have more than one radical in the equation, but they don't necessarily go away when you square both sides. All right, so let's look at this equation here. We have the square root of x plus the square root of x plus 2 equals 2. So I'm going to isolate the more complicated one first, okay? So that's the square root of x plus 2. I'm going to leave that on the left side, and I'm going to subtract the square root of x from both sides. Now, this is just the way I do it. It works it works either way. You can subtract that other one. I find that it's easier generally to deal with this because you end up with removing a square root and you get a much nicer solution here, rather than when we're squaring this, now we have to deal with intermediate terms that involve something that is perhaps more complicated. So it's not a rule as much as it is just a way to keep less writing. All right. Okay, so we'll square both sides, and now we have to be careful how we square this. So the difference of two terms squared is going to be The first one squared, the last one squared, and then this intermediate term is 2 times the product of the two terms. So 2 times 2 times the square root of x is 4 times the square root of x. And now we solve it from here, but we still have a square root. So the solution here to solving this is to isolate the square root. All right, so the first thing we'll notice that we have x on both sides that we can just subtract. And now what we do is we can subtract 4 from both sides. And now we divide by -4, and we get 1/2. So when we square that now, we have x equals 1/4. Okay, so everybody follow how I got from here to here? That's 2/2, or 2/4. The negatives cancel. And then I have my square root isolated, so when I square that, I square the 1/2, and 1/2 times 1/2 is 1/4. All right? Then you check it. Square root of 1/4 plus the square root of 1/4 plus 2 really isn't all that bad. 2 is 8/4, and so you add 8 and 1. You get 9 in the inside of the radical there, and you take the square root, and you get 1/2 plus 3/2 equals 2, and we're good. Okay? Any questions? All right, so it's time for you to try. Oops, I guess we want to do more than just... Okay, so this one looks a lot like the first one that I showed you, but it'll, you can refer to your notes, of course, and follow the pattern. Okay, so you're going to take the square root of t and put it on the other side. And now we square both sides. And notice the 2 t's just drop out. Okay, everybody get 1/2? Or at least see how to get it? Good, and we check it. Okay, now, there's one I'd like to write on the board for you to do. This one will be a little bit more challenging, but just stick with it. Okay, don't worry about that problem yet. I want to completely finish this one before we get to that one. So what do you think about that one? Anybody get a solution there? No? It's going wild on you?
Yeah.
Okay, so let's look at this, and it does get a little bit more challenging, but it's still quite doable. And one of the problems about, learning algebra is that you learn the principles, and then there's usually, problems that you do that work out to nice integer solutions and things of that sort. And then when you get to one that has a little bit more to it, then, it's harder to follow the principles of solving this thing, but you just have to stick with it. There's nothing new in this particular problem. It just gets a little bit messy on you. Okay, so the first thing that we'll do is take the this one on the other side. Like that. Okay? Fair enough. Now we'll square both sides. And so when we look at what this is squared, we say this is 9 minus 6 root x plus 1, and then this will be plus x plus 1. Okay? So then the next step is we're going to simplify this and try and isolate that last radical. Okay, so probably get this 10 minus 6 first. And then if we subtract x from 2x, we get x. And if we subtract 10 from 5, we get negative 15 equals negative 6 plus that. Okay? Now, next thing we have to do is then take the negative 6, and so we're good to this point. Right? Probably should have started over a little bit more this way. Anyway, now what we have to do is we have to square both sides, and this is where it gets a little bit more complicated. This side is easy. This is going to be all over 36, and then we take x minus 15 squared, so it's going to be x squared. And here's where knowing your form really helps. It's going to be 2 times 15 times x, okay? So we get negative 30x, and then 15 times 15 is 225, great. Okay, so now what we'll do is we'll multiply both sides by 36. Now notice I probably could have squared this and ended up with the same thing, right? It would be 6 times this x plus 1, or the 6 squared times this once we square it. And that's what I'm going to do first thing anyway. So it turned out that making that on the left side wasn't all that important. 225. And so we have 36x plus 36. Okay, yes?
Can you explain how you got the 6 in this second step?
This one here. Okay, so it's squaring this. So if we take 3 minus the square root of x plus 1, see what we're doing, since we're squaring this side, we're going to square this side. So we get 3 times 3 is 9. And then we get negative 3 x plus 1, and then negative 3 square root of x plus 1. And then this turns out to be plus x plus 1. And so that simplifies into that, which is what I had there. Okay?
Yeah.
All right. Okay, so now we're going to deal with this. So we have 30 minus 36 will give us negative 66x, right? And then we have 225 minus 36. So that's going to be 189? Okay, now we got to factor this. Of all the ways that you've learned how to factor, we look at these two and say, well, that's kind of in the middle. So it's not going to be 1 times 189, and it's definitely not going to be, if we look at roughly the square root of this thing, they won't add to 66, right? Because the square root of 225 is 15, and nowhere are we going to get 15 plus 15 equals anywhere close to 66. So we look at intermediate numbers. Look at the ratio between the two of them. We have 66 and 189. They're roughly 3 times. This is roughly 3 times this one. So if we say, okay, let's divide this one into 3, and what we get is 63. So bingo. Here is 63 plus 3 is 66. So we have x minus 3 and x minus 63. Okay? So that's a little bit of pulling the rabbit out of a hat when it comes to factoring numbers. But the other way to do it is to completely factor this. And so, you know, this is 3 times 21, which is 3 times 7. So we have, and then another 3. So we have 3 cubed times 7, and you have a maximum of 24 different combinations to choose. So it isn't, when you discard the ends, it isn't that bad. Okay, so we have 2 possibilities, x equals 3 or x equals 63. So we'll try the 3 first. 2 times 3 is 6, minus 5 is 1, square root of 1 is 1, 3 plus 1 is 4, so we have square root of 4 is 2, 1 plus 2 is 3, so this one's good. Now 63 is a little bit harder to do. So if we take 2 times 63, we get 126 minus 5 is 121, which is 11, right? And already we know it doesn't work because regardless of what this is, it's not going to be negative, and 11 is already bigger than 3. Okay, but let's try this anyway. We take 63 plus 1 is 64, square root of 64 is 8, and so that turns out to be 8. 11 plus 8 equals 3, and that's wrong. So this one is extraneous. Now, remember I was talking about how the cases that don't work, sometimes it's just a matter of the sign. Look at this. The difference between these two is 3, not the sum. And that's because somewhere along the way we're squaring something that and lost track, not lost track, but we essentially got the same answer as if that would have been a negative. Okay, a little bit longer, right? But it's still doable. There's no step in there that was different than anything that we've had before. All right, now, recently we haven't been dealing with word problems very much. Okay, we had a few of them, and I'm going to try and intersperse a few more as we progress. And here's one that involves a square root that, you know, is pertinent to the kind of thing that we're talking about right now.